Hello everyone, this is Alexey, and today I want to show you another tutorial on the Libra package. So today we are going to use it to read XML files. Well, as you know, many computational chemistry software start using some XML formatted um, files for storing their useful information. And I just learned that quantum-espresso is doing this, and as you run the calculations, you may um, generate the so-called save directories for the temporary files, and these directories will contain the basic information about your calculations. And here's one of the examples I saved here for you. This is the file I fetched from the X dot save folder generated by the quantum-espresso, and as you can see, it contains all the information that is relevant to this calculation. So all the general information, some parallelization information, and then the information on the input of the calculations, and what is most important, the formatted information on the output with all the properties, algorithmic, atomic species, coordinates, some other symmetry related information, and of course band structure and forces. So this is the band structure over here with the occupations and eigenvalues and the forces. So you can imagine many ways of using these sort of files. Now, we want to use, of course, we need to wait to read this formatted data into something that we can readily use, and that's where the Libra can be useful. So here I have set up an example file for this sort of calculations, and it will demonstrate one of the classes implemented in the Libra called the context class. So here we again just import the Libra core module to our Python script. Here I have preset up some function. As you can see, this is like a tiny function that would read this data file schema. Now what happens here? We first create this object of the context type with a file name that will fit, and as you can see, this is already the usage. So feed this data file schema .xml file to the to our routine. Now we generate this object of the context type. We set up the path separators. Essentially, if we wanted to tell this object how to access some information and data, we would need to provide some formatted paths to this data, and to separate different levels in the XML nesting, we will use the slash in the path names. So here we start with a simple instruction to print in the path where we are presently, and also showing the children of the topmost level, which is quantum-espresso. As you can see, well, actually we can start with this. So let's just start with printing the top level path where we are brought by this constructor. So I use the sequin, and here I'm going to in this directory, and that's where I will run this file. So that's where you can see this. Well, just ignore all this stuff. It's okay. You will often see this sort of output, but it's not a problem. So now you can see this path is quantum-espresso, which is the path of the topmost level in our XML nesting. So now we can use this information and show the children or the sub-levels of this tag by using this function show children. Okay, so now we use this and we run, and now what you can see, there are two special keys. One is XML attributes and XML command. These refer to this information. So the information like XSI, whatever it is, units, these are all XML attributes which has these values, and this is the comment. Now we also have other things like general info, parallel info, input, output, and let's look at this output. So and you can of course locate these sub levels here, so you can see the parallel info, input, and general info, right? So we are interested in the output. So let's go here, locate the output. Yeah, so here, and if we try to look or print its children, we will see convergence info, algorithmic info, and so on. So let's do this, and by doing this, we basically are continuing this output, right? So. And then you can run it again. We see all the convergence info, algorithmic. Let's look at the band structure. So we can do this band structure, and we get this. So whether it's non-collinear, whether this is spin orbit, coupling is included, number of bands, and so on, and then this quantum energies. So let's access this quantum energies, KS energies, right? And this will print the next level of indentation, and we can get, for instance, eigenvalues, right? So eigenvalues, and now if you can see, whoa. First of all, it gives us the error. There is no such node or tag eigenvalue, because I made a mistake. Should be eigenvalues, right? And then if we run it, we get that the only key left is XML attributes, and this can be found in the following place. So we can look at this level. We are here, eigenvalues, and then XML attributes would be the size. And actually, for this one, this is the only XML attribute that we can access. So we have 200 eigenvalues, right? Now let's access these energies to do some calculations with them. Okay. To do this, we will use the get function. Now, the get function takes the path to the data that we need, starting from the root. So our root directory is here, so we only need to use the rest of this path. So we'll go here, and this value, the second value, second argument here would be the default value returned by this function in case this node is not found. So we can also print the result of this function. So, and let me first make a mistake and say eigenvalue and see what happens now. It gives me -1 because that node is not located, is not found. Now let me do this eigenvalues, and instead of 1, I'm still getting 1. Okay, that's a strange thing. Eigenvalues. Yeah, so we don't need this first slash. We don't need this first slash, and then we get all these values as a single string. So this is just a string. To do something useful with it, we would need to convert it to floats. For instance, we can do res like that, and then we will do we can actually split this string, and then the rest will be a list of strings. So we can do print res, and then you can see something like that. So now we get the access to all the data, but still in the form of strings. So let's convert them to the floats, for instance, by doing this item in res, and then here we'll do 1212 print it, and then float of it. So that would be a conversion to the floating value point, floating point value. Yeah. So, and this is the result on 200 eigenvalues, and that's how you can use the context object. As you can see, it's very convenient. All you need is just a few lines of code and little post-processing, and then you can access any information you need from such complex files. And the good thing is that they do output all the information in the XML format, which makes reading it very convenient, especially if you have these utilities like Libra. So, well, let me actually, we have a little bit of time, so let me show you another, just to kind of to repeat our exercise. Let me access forces, right? The forces are located here, the same level as band structure, and then I would do pretty much the same. So I'll get forces here, forces. Now, and that will give me again a list of literals, all the, oops, not this one. Now here, oops, here I have -1, which means I cannot find the forces for the reason because it's at the level of band structure, not under the quantum energy. So I do it output / forces, okay, and then I should be able to get this list of data, and of course it will be like X of first atom, Y of first atom, Z of first atom, then we get X, Y, Z of the second, and so on. So then again I can split this information, I can combine them in triples, and that will give me an information about all forces in the system. So on that, I guess we can finish this tutorial. I hope it was useful for you, and you will find ways of using this context class of Libra in your applications. Oops.